Hello, everyone. My name is Zhou. I'm the CEO and founder of Quackchain. So today I will give in-depth insight of what Quackchain is doing from technical perspective. So the problem, right now everybody knows that actually the blockchain is suffering from the scalability problem. For example, compared to the centralized system, for example, Alipay last year, which is able to deliver more than 200,000 transactions per second, while a lot of blockchain, for example, Ethereum, can only deliver roughly 10 transactions per second at the moment. So this blockchain scalability problem greatly limits the further applications of blockchain. And so basically the problem is that it's extremely difficult to achieve three properties of a blockchain. First is decentralization, second is security, and scalability. So if we ignore one property here, for example, decentralization, then actually centralized world, for example, Google and Facebook has already achieved a great scalability to meet the internet-wide users' needs. One of the few systems, like for example, Google's Bigtable, also Cassandra. And if we ignore, for example, scalability, right now, like Bitcoin and Ethereum is working pretty well these days. And suppose we sacrifice our security, and one way is to create multiple blockchains and let them run in parallel. However, this blockchain can be easily attacked these days. For example, Bitcoin Go recently been double spending attack because of a low hash power on top of the Bitcoin Go. So in general, achieve this, both three properties will be a pretty difficult problem. And so before I introduce how Quackchain addresses the scalability problem of blockchain, so let me give a brief review of the scalability history, especially from the centralized world. So back to 2000, at that time, when people, before the internet, rise of the internet, people are trying to address the scalability problem by using what's called vertical scalability. The basic idea is to buy more expensive machines, CPU, memory, and put them together to offer higher performance. So there are a couple of companies that are famous in this area. For example, Sun is famous for its workstation. Oracle is famous for its database. And EMC is famous for its storage. However, with the rise of the internet, the services just grow exponentially because of the internet users just grow also exponentially. And all these vertical scalability solutions just quickly reach their limits because the physical limits of, for example, we cannot have arbitrarily high frequency CPUs. And also we cannot have an arbitrary large memory in a single machine. So new companies, internet companies like Google and Facebook, address this scalability problem using a new way called horizontal scalability. So the basic idea is to build a cluster of commodity PCs, where by adding more PCs into the machine and put them together and work on and service all the users, the system capacity just increases. And the core technology behind this horizontal scalability is called sharding. Now, in 2008, with blockchain, with Bitcoin, so in a decentralized world, we feel this is following the similar trend in what centralized world has been gone through. So for example, early solutions to address blockchain scalability problem is basically we call it vertical scalability, which basically improves single blockchain performance. So for example, there are two key parameters in the blockchain. One is the block size and block interval, where the Bitcoin has 600 block interval and 1 megabytes, up to 1 megabyte block size. So early improvement, for example, like a Litecoin, improved the performance by reduce the block interval from 600 to 150, which they can claim 4 times performance improvement. And Bitcoin Cash increased block size to 32 megabytes or even more, so that they can claim 32 times or even more performance improvement. And however, we cannot arbitrarily increase block size or decrease this block interval because there's a physical limit of network propagations, because the nodes are running in the internet global-wise. So new solutions try to address the problem by employing new consensus. For example, Ethereum using the Ghost algorithm, which is able to decrease the block interval to further 15 seconds. And new blockchains like for example, EOS, further decrease the block interval to sub-seconds by sacrificing only 21 nodes are able to produce the block. So we believe these vertical scalability solutions is approaching their limits, either sacrificing decentralization or posing a very strong constraints on network propagation limits. And we believe that in the future of blockchain, suppose the blockchain can reach some popularity that everybody is able to use the blockchain anytime, anywhere, then we believe that should require also horizontal scalability technologies, which we call it blockchain sharding. So what is QuackChain? So basically, QuackChain aims to address the blockchain scalability problem, which is a decentralized and secure, scalable permissionless blockchain, which can deliver very high on-chain transaction by using horizontal scalability technologies that are widely developed in the centralized world, for example, Google and Facebook. So our engineers, a group of engineers from Google and Facebook, which have extensive experience in designing, implementing, optimizing, and maintaining those large-scale distributed systems in Google and Facebook. And we are inspired by these technologies, and we carefully select all these technologies into the blockchain and try to address the problem. So currently, we have a testnet that is public accessible via testnet.quackchain.io, which is able to deliver more than 14,000 transactions per second by using sharding technology. Okay, so then probably there are a couple of questions raised up. So what is sharding? And why it is difficult to implement sharding to the blockchain? So sharding basically is a technology that partitions the system state into multiple substates, which we call shards, and process these substates relatively independently, so that as long as we can include more shards and also more processors or nodes, then the system capacity can be increases. And so there are also key challenges in blockchain sharding. The first challenge is how to partition the system state. And second is that how can we build consensus to drive all these substates or shards so that we can still be able to achieve security and decentralization. And third is that with multiple shards in the network, how we are able to enable interoperability, which is the interaction between different shards, and usability, which means that the user does not need to aware these constraints imposed by sharding. And these are several key challenges which we believe in the blockchain sharding. So first, let me introduce how we partition the system state and also compare how it is similarities with centralized system, for example, the famous Google's big table. So first question, what is the system state in the blockchain? So actually, the blockchain system state is essentially a key value store where, for taking Ethereum as an example, the key is basically address, is the address which is a RIP MD160 of the public key of the users. And the value actually is a key value mapping which contains the balance of the user, nouns, code, and storage. And for the key value stores, actually, there are several basic operations, which is called CRUD, create, read, update, and delete. And so basically the blockchain, no matter how the transaction it is basically a composition of all these operations. So now we have a good news that actually this is basic key value stores then we may be able to apply some experience from the decentralized system key value stores to address this problem. However, the bad news that a lot of this centralized key value store system, for example, Bigtable and Cassandra, they are more designed for raw CRUD operations. While for the blockchain, those operations are much more complicated. So for example, in Ethereum, there are basically two types of transactions. One is balance transfer. Basically, I send some Ether to another people, or calling a smart contract. So balance transfer basically involves two update or one update and one create operations. And for the smart contract, it is more complicated. It can be any combination of CRUD operations, which I can create a new smart contract. I can send also a balance to another user. I can modify the storage of another smart contract. So it's much more complicated. So we know that like distributed key value stores, like Google's Bigtable, HBase, or Cassandra, they can offer great scalability, which is able to serve billions of people in the world in the Google's and Facebook's data centers. However, they only support pretty raw CRUD operations, while for the blockchain, it can be any combinations of CRUD operations, which means that suppose those keys or this data, they're partitioned in different shards. And if we want to perform a transaction and also ensure the atomicity between this data in different shards, that will be extremely difficult, even in Google and Facebook. And it requires proper cross-shard transaction coordination. Like for example, Google, they implement kind of atomic clock, a GPS clock in most of the machines, so that they can guarantee that the time ordering of these transactions, which is very expensive. And in addition, suppose there are a lot of transactions that running across over multiple shards, it can even worse the scalability. So the whole system can be even runs even slower because the overhead of the cross-shard transactions. So to address this problem, so we further basically introduce a concept called shard key in the system, where the address consists of the original address, which is the Ethereum's RIP160 public key, plus another shard key, where this shard key is basically a 32-bit integer to tell us where the key value data, the user account or smart contract, should be partitioned to. And for the user, since it has only its private key can successfully decode corresponding the public key, it's able to manage all the addresses of the same we call recipient, which is the first 160 bits in all shards. And so given this address and its shard key, and also the shard size, for example, I have 256 shards, then we can easily determine where the key value pair should be partitioned to by taking the modulus operations on the shard size. And in addition, we also encode the shard key as the key value, as the value into the state, so that we know that where the data should be partitioned when there is a repartition event we all call reshard, which is also critical operations in the blockchain in sharding to add more shards into the network. So with this shard key, then we can easily better to define different kind of transactions to see whether this transaction will touch multiple states in different shards or not. So for example, for balance transfer, if this transfer happens only in one shard, which means that the source and destination addresses are in the same shard, which this is basically an in-shard transaction, and this is very efficient and can be performed very quickly. However, if the source and destination belongs to different shard IDs, then this is called cross-shard transaction, and then we need further coordination to address this problem, which I will explain later in the interoperability. And for smart contracts, that will be a little bit more complicated. And to simplify this scenario, the blockchain only allows this smart contract calls happen in the same shard, which means that the caller and the callee, which is a smart contract, must be in the same shards to avoid this overhead of cross-shard transactions. In addition, to avoid this smart contract being repartitioned because they have dependency relationship, any smart contract calling another smart contract must have also the same shard key. This will make sure that no matter how the network being repartitioned, all these smart contract with the same shard key will be always in the same shard, so make sure they are always behave consistently. In addition, with this shard key, we can also doing reshard to add more shards by splitting one shard to multiple shards, which in this way, we can significantly reduce the data migration cost. And as a result, this will double the number of shard size of the system, which means the system capacity can be doubled after these reshard operations. And one key question during this sharding design is how to choose this shard key in Quark chain. So if, for example, a smart contract depends on another smart contract, for example, a user runs a crowd sale and which depends on one ERC20, then they must have the same shard key to make sure that this kind of dependency transactions can always succeed. However, if the smart contract does not have any dependency, then the creator is free to choose any shard key that the system can impose some rule. For example, using IP address of the shard key so that we know when we deploy these shards, it is related to some local information there. So with this shard key design, actually we can compare like the similarities of Quark chain versus Bigtable, which is Google's famous key value store. And so we have a lot of similarities compared to Google's Bigtables. First, we basically shard by one called shard key, or Google called row key. And then for any key, the data actually is a mapping from Quark chain is basically recipient to account data, while the Google's Bigtable is basically row key to corresponding arbitrary data. And as long as the transactions, for example, smart contract transactions happen in the same shard key, then we can guarantee the atomicity of the transactions because they will always happen in the same shard. And Google's Bigtable also ensure the atomicity as long as these batch operations, they are operated in also the same row key. Besides these similarities, actually we have also some improvement or difference compared to Google's Bigtable. So first, Quark chain natively support cross-shard transactions by moving the balance from one shard to a different shard, while Google's Bigtable doesn't support cross-shard transaction. In addition, we allow reshard by splitting the shards to two shards, while Google's Bigtable allowed merging operations because of the deletion operations. Okay, so besides a partition, after partition, this basically is a system state to multiple substates, which we call shards. The next question is how to build consensus to drive all these shards in a secure and efficient way. So a simple way to address this problem is to build called a sharded blockchain, which basically each shard, including in substate, are processed, are driven by a blockchain using some kind of consensus, for example, proof of work. However, this quickly becomes a security issue because we call it hash power dilution, because it's supposed to have 100 shards and each one using proof of work. That means that the hash power to one of a shard will be 1 over 100, which means that it can be easily attacked by 51% double spending attack, similar to what Bitcoin Go has happened before. To prevent this case, Quark chain basically introduced a root chain, which basically have two properties. It does not process any transactions in the network, but its purpose basically is just confirm the header of each sharded blockchains or sharded blockchain blocks. And second is that it will have sufficient incentive so that it has sufficient hash power And any attack of these transactions on this sharded blockchain, because of this our consensus, it must also attack the root blockchain, so that which means that the cost of being attacking this sharded blockchain will be also expensive. To have more details, basically, a root chain runs a consensus which we choose can be proof of work, proof of stake, or even DPoS. And it's basically, for each block of the root chain, it just contains the longest chain that has not been confirmed in each shard by an incentive, where its block reward equals the Coinbase reward plus the summation of all these blocks, sharded blocks that is collected times alpha I, where the alpha, we call it as a tax rate. Which means that basically every shard in this block, its block reward will be 1 minus alpha times the corresponding block reward. And so that the root chain is incentivized to include the longest chain of each shard to achieve maximum incentive. And for each shard, it basically runs a consensus called root chain first consensus, which means that for each shard, when there's a two fork exist, it will compare which fork of the shard has the longest root chain that has been confirmed before it compare its length. And for those parts that are not confirmed by the shards, basically it will use in the basis consensus either proof of work, or proof of stake, or DPoS. With this root chain first consensus, we can guarantee that as any transaction being, for example, confirmed by the root chain, any double spending transaction must also attack the root chain, which needs significantly cost in terms of, for example, hash power or any other property like DPoS require, for example, more than 1/3 of this being malicious nodes. And with this structure of this consensus, actually also Quackchain opens some possibility of the new attacks. So there are several attacks actually we have a thorough analysis, including double spending attack, blacklist attack, stealing attack, and bribery attack. And here I just give an example of how double spending attack is being performed in the Quackchain, which I just mentioned that in order to attack a transaction in the shard, because of the root chain first consensus, the attacker must also create a longer fork in the root chain so that it can override the transaction, revert the transaction in the shard, and both the shard and the root chain, which means that it needs some significant amount of hash power there. And actually, Quackchain is not just a single consensus. It's a class of consensus built on top of these two layers. So for example, one example I also mentioned a lot is regarding the root chain and both the shards, they run called proof of work. And we call this kind of consensus called collaborative mining. And then we can adjust the hash power of the root chain by adjust the tax rate so that we can determine how much incentive I contribute to the root chain over the whole network. We are also be able to, for example, implement different consensus in different shards. For example, we have the root chain running proof of work, and some shards run proof of stake. This allows more hash power can be allocated on the root chain. And even we can run like a mix of consensus. Some of the shards run proof of work, or some of the shards run proof of stake. And even we can also change the consensus where the root chain runs DPoS, while each shard runs, for example, proof of work. And so now, with this ledger and also the consensus to drive all these transactions, the next question is how the user is able to, for example, use interoperability to manage all its resources in the network. So the basic goal of the interoperability is that the user, which maybe have multi-balance in different shards, is able to access all the resources in all shards, including, for example, calling smart contracts in different shards, and also transfer if balance to another address in different shards. And this is achieved by cross-shard transaction, which I mentioned before, which is defined to move the balance from one shard to another shard. So in the blockchain, we designed this cross-shard transaction as our first-class citizen, which means that first, it's very highly efficient. Any user is able to issue the cross-shard transactions by moving its balance to another shard anytime, and this procedure is confirmed in minutes. And second, that this cross-shard transaction is scalable, which means that the number of the transactions per second over the networks increases as the number of the shard increases, which is a very important property of the blockchain. In addition, to minimize the user's knowledge of this corresponding sharding, for example, cross-shard transactions, we create a smart wallet applications which help users to manage its balance among different shards and call transactions among different, call like smart contracts in different shards, like smoothly. And then this wallet will automatically tell user, hey, how much balance you need to call to a destination smart contract and how to move its balance, and also collect this balance if there's too many balance in different shards and put them together into a single shard. And here is basically some pictures of what the smart wallet looks like. Okay, with this interoperability and also like partitioning and consensus, another question is the usability. In terms of usability, one thing we found in the sharding is that actually also like in terms of Ethereum is that there are a lot of limitations of the ERC20 token. So for example, if I want to use an ERC20 token to make a smart contract payment, that's really complicated. The user needs first to approve some amount of the ERC20 token to a target smart contract, and then call corresponding contract to consume this approved balance. And then third, and also optionally call approved zero to make sure there's no, for example, kind of called exploit attack. And this is very inconvenient compared to native token, for example, Ethereum, to perform a smart contract payment transaction, for example, cross-sell. Because a user can just perform cross-sell by sending its Ether, and they can get corresponding token back just automatically with a single-step payment. And second issue that it's very hard to use ERC20 as gas. From miner's perspective, it just ran all the transactions and according to the gas price and determine the value of the transaction and include it in the block. However, there are several ways try to say, hey, using ERC20 as gas to make the payment or make a transaction. However, it's still pretty complicated because the miners need to run the transaction in order to determine how much reward can be accepted in terms of ERC token or other tokens, which is rather inconvenient for the miners. And third is that using ERC20 for sharding has a lot of limitations in the interoperability, because this ERC20 is reside in one smart contract. And in order to move this ERC20 token to one shard to another shard, then we have this smart contract to coordinate together, which is very complicated. So to address all this problem, blockchain will basically propose called a multi-native tokens. Basically, the user is able to create native token on top of the blockchain. And each native token will be associated with a unique ID into the blockchain. For example, in the blockchain, QKC will be the first native token, which we call Genesis native token. And people can create other native tokens like Apple, Orange, as they want. And in order to, when doing the payment or transactions to smart contracts, the user can just specify which kind of native token to transfer to different destinations by providing the ID and also the target addresses. And also, with this native token feature, the quadchain is able to support moving these native balance tokens from one shard to different shards. So with this native token, basically to support these native tokens, a transaction basically needs to have an additional 2 fields to include which native token is used as gas and which token is used to transfer the basic transfer to the destination. And from miner's perspective, it will be much easier to determine which transaction to be included in the block by just ranking all the transactions by their gas price times their fiat price of the gas token by connecting to an external price oracle, like for example exchange. So they can determine the value of this transaction much easier without pre-evaluate all these smart contracts transactions using ERC20 as a payment. And to support this multiple native token, the virtual machine itself must also be aware which tokens we are using in the gas, and also which token is transferred during the smart contract transactions, and also is able to change the token that is being transferred during the during the token in the subroutines. So with this, for example, we can easily create a crowd-sale that using a user-created native tokens, accepting user-created native tokens to buy another new native tokens easily. So for example, here example of Solidity example, where in its callback function, it basically says, hey, it only requires accepting only Apple token. And then once checking the corresponding capacity of the crowd-sale and also individual capacity, then it can just determine how much value can be buy from these transactions, and then transfer another token, which is orange, from the smart contract to the user who sent these transactions. So to complete this crowd-sale, the user just needs to send a single transaction by specify the target address with Apple, tells, hey, I'm going to pay the Apple with corresponding the value, number of the Apple's token I want to pay, and then it's done. There's no need to approval, there's no need to other operations. And this can greatly simplify a lot of D apps if it wants a single transaction to complete the rest of services atomically. So besides all these improvements of the quadchains, there are other core features. So one is that the quadchain is completely EVM backward compatible. So actually the quadchain itself can support multiple virtual machines because different shards can run relatively independently using different consensus and even virtual machines. And another important feature is that it's able to scale the supernodes by using horizontal scalability technologies so that an expensive superfull node, can be replaced by a cluster of the honest small nodes and put them together, and then to process all the ledger, including all the shards and root chains, efficiently. Okay, so this is I finished the basic technical overview of the quadchain. So let me introduce a little bit about our latest testnet results. So we launched our public testnet on July the 2nd, which contains a network with 250 shards and with 50 clusters. And each cluster has 129 nodes. And so the whole system is running more than 6,000 nodes. And all these nodes are basically deployed over the world, including United States, Singapore, and European. And so we actually have a periodic load testing which generate 3 million transactions and flood this transaction to the network every 8 hours. And every user is able to watch what the results, and they achieve more than 14,000 transactions per second. And so thank you very much for attending my presentation. And of course, we are hiring, and then let me know if you have any questions.
네, thank you, Mr. Zhou. So 치조 대표님에게는 여러분이 어떤 질문을 해주셨는지 함께 살펴보도록 하겠습니다. 첫 번째 질문입니다. How blockchain guarantees that there are at least one running shard all time?
Yes, this is the same question. Is that how to guarantee there's only at least one cluster running or one full node running in the network? And I think this is the same question probably to for example, Ethereum and run also any P2P network. Basically, it needs at least one node to make sure the network is alive. So definitely, we ourselves will run some seed clusters in the network. Each cluster will basically process all the transactions in all the shards. So this guarantee that there's at least one, as a bootstrapping stage, there's at least one shard being run in the network.
네, 시간 관계상 Q&A는 여기서 마무리 짓도록 하겠습니다.